Hi everyone, this is uh, Prakash here from Emerging Open Tech Foundation, and we are into the question 5, which is for the module M03 part 2, and Jaymeet Vasava is going to today focus on ML using Python with hypothesis testing, which is what the topic is related to machine learning, and it includes part of the data science because we need to address that. And so with that, I will hand over to our expert, Jaymeet Vasava, our instructor, who has been doing the diligent work of presenting. At the same time, those who are interested in watching it on the YouTube are welcome to watch it, as well as you can connect to us if you need anything other than that. Thank you very much, Jaymeet. Take over from here and welcome to uh, complete the session. Fine. Thank you.
Thank you, sir. And hello, everyone. This is Machine Learning with Python. This is Module 3, Part 2. In the Part 1, we discussed about different distributions like normal distribution, exponential distribution, Poisson distribution, and their uses and stuff. In this session for Module 3.2, we'll be discussing about hypothesis testing, and we'll be discussing about different tests like one sample Z test, T test, two sample T test, then pair test, and analysis of variance and stuff. But so this is our goal for this session, or learning objective for this session. So before we move to the hypothesis testing, we have to be familiar with the central limit theorem. Now there is a lot of text for this, but let me just brief you for the central limit theorem. Let's say there is a population, and from that population of data, we are making few identical samples, or some numbers of identical samples. Now those identical samples will be having the mean and the standard deviation of the population as well. Now that, and it will follow a normal distribution. So this is somewhat what the central limit theorem says. So for the purpose of denotation of the symbols used for central limit theorem for the population data and the sample data, first we have the mean population denoted by mu, then the standard deviation denoted by sigma. Then for the samples standard deviation, we simply use sigma by square root n, and the mean will be denoted by capital X. So as we have the population's mean, the whole data set's mean, we have the standard mean for the population as well as standard deviation for the population. The same goes for the sample size, the sample that we are drawing from the population data. So we have the sample size for it and the sample mean for it, denoted by capital X. The sample size is denoted by n, and then comes the sample's standard deviation, denoted by capital S. Now this is what shows or depicts the normal distribution. So central limit theorem says that when a large enough sample size is taken from any distribution with a mean and variance, the distribution of the sample means will approximate a normal distribution regardless of the shape of the population distribution. So now, as we have familiarized ourselves with the central limit theorem, let's start with hypothesis testing. So hypothesis testing is nothing but if I try to introduce you with hypothesis testing with a normal analogy of a day-to-day life, let's say that we have a belief. That belief will be based on our past experience or past data, and we create a belief regarding that. So our current belief will be called as a null hypothesis, and anything that changes that null hypothesis or in opposed to that null hypothesis will be called as alternative hypothesis. Null hypothesis will be denoted by H0 and alternative hypothesis will be denoted by HA or H1. Now, an example for a hypothesis will be because there are clouds or because there is a cloudy weather, it will be raining. But it is not necessary, and when certain kind of uh, figures or numbers are presented which invalidates our null hypothesis and says that it is not necessary that because it's cloudy it will be raining and supports the alternative hypothesis, then we reject our null hypothesis. So hypothesis tests are broadly classified into parametric and non-parametric tests. What are parametric tests? They are population parameters of distribution such as mean, proportion, standard deviation, etc. So they take care or they focus more on the parameters like mean, standard deviation, and stuff. The non-parametric test, they do not take into consideration of the parameters, but about other characteristics such as independence of events of data following certain distributions such as normal distribution. So what do you mean by independence of events? It just simply means that one event occurring should not have an effect on the other events, other similar kind of events occurring. So when we flip a coin, one flip should not be, or a flip one should not be affecting flip two. So every flip that we do are going to be independent, and the probability remains same for all the events. So some of the hypothesis test examples. First, we'll take the medical example or null hypothesis says a new drug does not reduce blood pressure. Alternative one says the new drug reduces the blood pressure. So what we mean is the null hypothesis assumes no effect of the drug, while the alternative hypothesis suggests the drug has an effect on the blood pressure. An educational example will be for null hypothesis, there is no difference in test score between students who received tutoring and those who did not. The alternative one says that students who received tutoring have higher test scores than those who did not. What do we mean? The null hypothesis assumes no difference in test score, while the alternative hypothesis suggests tutoring has a positive effect. Then comes the business example. For null hypothesis, the mean weekly sales of a new product are equal to the mean weekly sales of an existing product. The alternative one says the mean weekly sales of the new product are greater than the mean weekly sales of the existing products. What do you mean? The null hypothesis assumes no difference in sales, while the alternative hypothesis suggests that new product has higher sales. So there will be, so as we'll be conducting some of the hypothesis tests, we'll be discussing about a normal framework that you can follow in order to conduct the hypothesis test. So the steps to conduct or this steps under a normal framework of conducting a hypothesis test. What the first step would be to define the null and the alternative hypothesis. Hypothesis is described using population parameter, that is mean, standard deviation, etc. So normally H0 is used to denote null hypothesis and HA or H1 for alternative hypothesis. Then identifying the test statistic to be used for testing the validity of the null hypothesis. And for example, there will be Z test or T test and other kind of tests that we are going to discuss in this session. So what do we loosely mean about point 2 is that there has to be certain kind of threshold which tells us or which acts as a reference for us that whether if we calculate and the value comes out to be lesser than or greater than, then that should prove us the validity of the null hypothesis or the alternative hypothesis. So going further with the third step, decide the criteria for rejection and retention of null hypothesis. So that's what I meant when I was trying to describe point 2, that there is a value called the significance value and it is denoted by alpha. Alpha's value is typically or conventionally taken as a 0.05 for normal case studies, but it can differ if uh, if the case studies are based on very critical studies like medical studies. So uh, in those points, the alpha's values are taken more low or more smaller. So calculating the probability value, which is the conditional probability of observing the test statistic value when the null hypothesis is true, we will use the functions provided in the scipy.stats module for calculating the probability value. Now, taking the decision to reject or retain a null hypothesis. If the probability value is going to be greater than it has its own meaning and lesser than it has its own meaning. So when we compare the probability value with the significance value or the alpha's value, if the probability value is smaller than or equal to alpha, we will reject the null hypothesis. Otherwise, we'll be retaining the null hypothesis. So what do you mean by the significance level or the alpha value?
Can you repeat the null hypothesis a bit? Because
Sorry?
can you repeat the previous null hypothesis a bit? Yeah, because the recording I thought was a bit.
Just a second.
Go ahead.
So the whole point or the fifth point or something? So
Just repeat null hypothesis this page. Okay, thank this slide. Thanks.
this whole slide, right?
Yeah.
Okay. So so we will be So this is nothing but a framework that you can follow in order to for carrying out the hypothesis testing. Now you can be bit flexible also depending on this case, but you can loosely follow it for the reference of conducting an hypothesis test. So the first point is defining a null and a alternative hypothesis, and the null hypothesis is denoted by H0, and alternative hypothesis is denoted by HA or H1. Then identifying the test statistic to be used for testing the validity of the null hypothesis, for example, Z-test or T-test. Now, these are the tests that we are going to be discussing. So, those are the tests that you have to identify, and we'll be discussing when and where to use it. Then, the third step is decide the criteria for rejection and retention of a null hypothesis. Now that has to be a value which tells us for reference whether the hypothesis or the or the current belief or the null hypothesis that we have should be retained or is valid or not. So this is what this significance value tells us, or alpha's value tells us. Typically, we take alpha as a 0.05, but we can also take alpha's value more smaller for much uh, critical experiments and insights. So like medical ones, because we are directly treating a human on it and a human life depends on it. So in those kind of situations, alpha will have the value much smaller than 0.05. For calculating the probability value, uh, will be so to calculate the probability value, which is the conditional probability of observing the test statistic value when the null hypothesis is true, we will use the functions provided in the scipy.stats module for calculating the probability value. Now, fifth is the taking the decision whether, depending on the probability value that we got for our experiment, we we reject or retain the probability value. Now, comparing the probability value with the significance level or alpha, if p or the probability value is smaller than or equal to alpha, we reject the null hypothesis, else we retain the null hypothesis. So going further with the significance level or the alpha that we discussed, a commonly used significance level is 0.05, as I also mentioned, which means that there is a 5% chance of rejecting the null hypothesis when it is true. This value is chosen based on convention and is considered an acceptable risk in many fields. The significance level is not calculated, but rather chosen by the researcher based on the context of the study and the consequences of making a type 1 error. Now, you can treat this as a confusion matrix, but what we mean by type 1 error is false positive errors. The values that were supposed to be negative but are falsely claimed as positive. The second error is type 2 error, which are false negatives. The values, those were supposed to be positive but are falsely claimed as negative. So, about the significance level, it depends on the first point states that it depends upon the research and the experiment being conducted or the test being conducted. lower the significance level require a stronger evidence to reject the null hypothesis, which reduces the risk of type 1 error but also increases the risk of type 2 error. The choice of significance level depends on the research question, the potential consequences of making a wrong decision, and the standards of the field. In some fields, such as medical research, a lower significance level like 0.01 may be used due to the serious consequences of type 1 error. In exploratory research, or when the consequences of type 1 error are less severe, a higher significance level like 0.01 or like 0.10 can also be used. Once the significance level is chosen, it is compared to the probability value obtained from the hypothesis test. If the probability value is less than or equal to the significance level, the null hypothesis is rejected in favor of the alternate hypothesis. If the p-value is greater than or the probability value is greater than the significance value level, there is insufficient evidence to reject the null hypothesis. So just to summarize, it depends on which the study is being conducted and the hypothesis test is being conducted, and on based on that or the fields uh, or the field of reference is taken, whatever significance level is taken in the field is taken for as the alpha's value, and depending on the consequences level of type 1 error, the value of alpha is chosen. So alpha value of 0.05 or whatever it is taken, it is not a calculated value but rather conventionally accepted values. So moving on to the first test called z-test. So z-test is used when we need to test the value of population mean given that the population variance is known. Next, the population is a normal distribution and the population variance is known. So we know the mean and the variance. The sample size is large and the population variance is known. That is, the assumption of a normal distribution can be relaxed for large sample size of n equals to, n being greater than 30. So for carrying a z-test, it is good that we better have a large sample size or at least larger than 30.
So population refers to the uh,
Yes,
entire samples, right?
yes.
Got it. And so
So population is referring to the whole population's data and the mean and variance. But out of that, we take out identical samples which also have the similar kind of mean from that population's mean and standard deviation.
so we eliminate basically the outliers, correct? That's my understanding.
Y-
Yeah.
Yes, in a way.
Okay, thanks. Go ahead.
Yeah, yeah. So the Z statistic is mathematically represented by the sample's mean denoted by capital X minus mu denoted by population mean divided by sigma, which is the population's standard deviation, and sigma divided by square root of n, which is the sample size. Now we'll be implementing this very formula in Python in order to get the z-test. So we'll be understanding z-test with an example of passport applications being submitted and is processed within 30 days. So let's read out the question first. A passport office claims that the passport application are processed within 30 days of submitting the application form and all necessary documents. On processing time of 40 passport applicants, the population standard deviation of processing time is 12.5 days. So we conduct a hypothesis test with alpha equals 2.05 to verify the claim for, of the passport office. So our null hypothesis says that our mean is greater than or equal to 30, and our alternate hypothesis says that our mean is smaller than 30. So first we'll be importing the math module in order to get the square root, in order to use the square root function. And with that, we'll be defining a function called z-test, which will take two parameters, which are population mean and the standard deviation of the population and the sample. Then we implement the formula for the Z score that we stated before, and you can see that on the screen right now. So we are simply implementing the Z score and then returning the value of the Z score, and also using the stats.norm for normal distribution for cumulative distribution function on the Z score. So when we use the Z score for our own for our given use case or for our given case, and gives them the argument values for a population mean of 30, standard deviation of 12.5, and our sample or the data that will be used. So that will be created as passport DF, and from that DF we'll be taking the data from the processing time column, and the output that we get is a minus 1.49 for the Z score and 0.06 for the probability value. Now here the Z score is greater than the, just a second. Here the Z score of minus 1.49 is greater than the Z statistical value of minus 1.64, and 6.77 is the probability value that we get. Sorry, 0.0677 is the probability value that we get. So 6.77% is greater than 5% of the alpha value that we have taken. So the null hypothesis is retained and can be concluded that processing time of passport is greater than 30.
Yeah, coming to that, we chose hypothesis that passports office is not processing less than 30 days, right? Within 30 days, correct?
Yeah.
That was the null hypothesis.
Yeah.
And at the end of what we find is that is true.
Yes.
So therefore, this result you have taken. Now, one thing I wanted to know, how did you choose those 30 samples? Again,
Sorry?
how did you choose the 30 samples? Is it like your set was thousands?
Yeah, the set already contains those
No, is there
those
any
values, and the question also contains that.
So okay, so when you give the sample, whatever the survey sample to the passport applicants,
Yes.
they mark, and if you have taken 100 samples, you only select 30 out of it, right? So is there any selection criteria, or just randomly you take it? Is it random, or is it some?
So here 30 is the mean,
Okay.
and not the sample size.
Okay, okay, got it, got it. So you are only
Yeah.
processing.
We can, so if we have taken for let's say 36, then it will be square root of n, so 6, and the calculation will be based on that.
Okay, I got confused. So the processing time is 40 passport applicants you have taken anyway, correct?
Yeah.
It's not 30, and so yeah, okay, got it. 30
Yep.
is the, yeah, it was a bit confusing. So thank you for a clarification.
So just a second. So this was the question that we were discussing. We had the mean of 30, standard deviation of 12.5, and the sample size was 40. The sta- the mean for the sample was not given to us. So that's what we calculated. So we got the we imported the necessary libraries. Then we read our data set and named it passport df for our data frame. This is what the first 5 values of the data frame looks like. And if we print uh, every values of in the processing time for the passport passports data frame, these are the values that there are
So question
now.
here, question here. So you are using Panda's data frame besides the sci-fi stats. Is that what?
Yeah, scipy stats are used for using this
Calculation.
stats.norm.
Okay, okay. So both of them you are using data frame as well as sci-fi. Yeah, good. Thank you.
Yeah, the Seaborn and matplot will be used for the use. So they are just imported here for the whole session.
So one is for plotting matplot, and what about Seaborn?
Matplot and Seaborn, both of them will be used further in the session. So that's why they are included over here. So is the warnings and stuff. So as we needed a square root for the application of this formula, we made the z test as our function, and then these are the parameters that it takes: population mean, population standard deviation, and the sample. The set score will be calculated like this, and the value will be returned to the function, the z, which are the z score value, and the stats model will be used for the normal distribution of cumulative distribution function for the z score. So given the values that we have, 30 for population mean, 12.5 for deviation, and the sample from here, we get the value of minus 1.4925 and so on for our z score value, and this is our probability value of 0.0677 or 6.77%. So so there is no not enough evidence to reject the null hypothesis. So we retain the null hypothesis. Now Now there is a left tail and a right tail test in the Z score. So the left tail set test will be used when the hypothesis test if the parameter like mean is less than a certain value. Example being testing if the average processing time is less than 30 days. The right tail test used when the hypothesis test if the parameter is greater than a certain value. Like for our example, testing if the average processing time is greater than 30 days. Then the two-tailed test is taken when the parameter is different from a certain value, could be greater or less. Now, moving on further with the one sample t-test. Just a second. So, okay. So, for the left and the right tail test, what it differs from the two tail test, for the right, we said that it can be greater than 30, and for the left, we said that it can be smaller than 30. But if there is a value that we don't know whether it's greater than or smaller than, so at that time, we can use the two tail test, and you can see by the null hypothesis and the alternative hypothesis that which states mean being equal to 30 and the alternative stating mean being not equal to 30. Moving further with the one sample t-test. One sample t-test is used and when we don't know the population's standard deviation. And so it will be estimated by the sample standard deviation, which will be denoted by capital S. So mathematically representing t statistic is equals to x bar minus mu divided by samples sample standard deviation divided by square root n. Now, as similar to the previous example, we will be understanding the one sample t-test with a new example as well. So the new example simply states that if we want to make a Bollywood movie, we need or we require 500 million or 50 crore on an average to make a movie. So, so we'll be using the dataset which contains the production cost of 40 Bollywood movies in millions of rupees and conduct a hypothesis test. We'll be using the value of alpha as 0.05 as well. So our null hypothesis says that the mean value should be equal to 500 and our alternative hypothesis test says that mean value is not equal to 500. So we'll be using the scipy.stats t-test method, which will be taking two parameters. One is an array-like structure for the sample of the sample or the data that we'll be using for it, and also the second one being the population's mean. Now, for our Bollywood movies data set and giving the population mean value of 500, we get the output of minus 2.28 for our t-test value and for t-statistic value and the probability value of 0.02. Now, let's see the notebook. So we wanted to know the standard deviation for the population mean being 500 and the number of samples being 40 from the samples data set. So this is how we'll be reading the data set that we have. If we print the values of the production cost, these are the values that that come out. And when we use the t-test model for our Bollywood movies for the data and or 500 as the population mean, we get the t-test result of t statistic being minus 2.28 and the probability value of 0.027. So this implies that the sample mean is less than population mean and has only 2.7% probability of being part of the distribution. So as p-value is less than 0.05, we can conclude that the sample mean rejects the production cost is equal to 500.
This one does not conclude whether it is more than 50 crore or less than 50 crore. Is that right? Because the testing is only for whether it is 50 crore, right? Exact.
Yeah, testing is whether it's 500 or not, or 50 crores or not.
50 crores or not. So it's not giving any decision whether it is more or less. More often it is more or less.
Yes.
That is not coming out of it.
Yes.
So it is the third one, not the right one. We test right wing and left wing, and what is that? Right tail.
Yeah, two-tailed one.
This is a two-tailed one. Okay.
Yeah.
Okay. So this is two trailed tests and with one sample t-test. With one sample.
Yeah.
Yeah, sample test. So you have any examples further for two sample or something? Let's move. Yeah. Sorry, I should not stop you. Go ahead.
Yeah. So as you have been observing that we are getting the minus values for the scores and stuff. So what does the positive and the negative t statistic values mean? So a positive t statistic indicates that the sample mean is greater than the hypothesized population mean. So the greater the positive t statistic, the more the sample mean is above the population mean, measured in terms of standard errors. So for our from this we can say, as sir also mentioned, that it does not sir asked that it does not say, but actually the negative and the positive signs of the t statistic values say that whether it's more or less. So greater the positivity statistic, more the sample mean is above the population mean, measured in terms of standard errors. If you are testing whether the average test score of a sample of student is different from the population mean of 80, a positive t statistic suggests that the sample mean is higher than 80. The negative t statistics means that the sample mean is smaller than the population mean. And taking the same example, that if we are taking the height of people and the population mean is 80 and we get a negative value, it means that the sample suggests the mean is lower than 80. So for here, if we take the interpretation of it, the value that we need for or the samples is smaller than 500 or 50 crores, 500 million INR or 50 crores.
Oh, you mean it is less than 50 crores?
Yes.
Oh, okay. Okay, I got it now. So
Yeah.
even though
So,
it is
it's the interpretation depending on
probability.
the mean populations mean that we have and the t statistics value that we get.
Good. Thank you for the clarification.
Yeah.
Next is a two sample t-test, which is required to test a difference between two population means where standard deviations are unknown. So the parameters are estimated from the samples. Now, in this one, we'll be taking an example of children with two groups, one which take health drink and one which does not take health drink. And what we have to observe is that which which uh, which sample, which is uh, one that drinks or one which does not drink, shows an increase in height or an average increase in height.
So you are dealing with two groups, one group with the drink and one without drink, that is,
Yeah.
and trying to project whether it is really effective or it's just a uh, hypothesis that it is not correct, right?
Yeah.
Thank you.
So in this also we'll be taking the alpha as the value of point. For alpha, we'll be taking the value of 0.05. Our null hypothesis states that drinking health drink will increase the height. Our alternate hypothesis says it will not increase the height. So we will be taking two groups from the health drink dataset that we are using. So one has the one which drinks health drink, we call it health drink yes DF for data frame. Then for no, for the group that does not drink. And when we print the first five records for the from the respective data frames, this is what it looks like. So when we plot the values of yes and no on data frames, this is what the plot looks like. We'll be using a histogram plot. And also when we run the t statistics for two sample t test, the value that we get from the data set that we'll be using, we get the t statistic value of 8.13 and the probability value of 0. So this is the statement that we are trying to check the hypothesis test on. We are reading the data set, then printing the first five values for it. Then for plotting the plot that we saw on the slides, this is the how the plot we get for the yes and no drinks. For the height increase and the density, you can plot it like this using the histogram plot through SN. And when carrying the t statistics or the t test for independent values of height increase and the height on for yes and no data frame, these are the values that we get for the t statistic value of 8.13 and the probability value of 1.19. But have a look at it that it's exponent to minus 13. So for the first values, we can say it's 0 for the first few decimal points. So we can say that the people who or the children who drink health drink is the increase in height for those who had health drink is significantly different than those who did not drink. Now, moving further with the sample t-test.
Before we move in the back,
Yeah.
so the histograms are bar plots, but these lines, is there a code there which draws that average?
So, are you talking about the disk plot and the his plot?
Yeah, his plot is this. What is this one?
Yes.
This comes by
So,
which code?
actually, you can use a disk plot, which is the distribution plot, but
Oh,
the Seaborn is going to remove that feature in further updates. So
okay,
that is the reason I'm just keeping here as a reference. But in whenever I am implementing it, I am implementing it using the histogram plot.
okay, good.
Yeah,
Thanks. Yeah.
yeah. So just for the time when we are recording this session, the disk plot feature is still available. So if you want to use it, you can use it right now. But it will whenever you will run it, it will also show a message about the feature being removed in the further updates. So moving further with the pad sample t-test, a pad sample t-test is a statistical method used to determine if the mean difference between two sets of observations is zero. It is commonly used in situations where each subject or entity is measured twice, resulting in pairs of observations. So, usually measurements are taken under different conditions, and the null hypothesis states that the true mean difference between the paired sample is zero, while the alternative hypothesis assumes that the mean difference is not equal to zero. And in order to understand this, we'll be uh, using an example where before and after the breakup, the alcohol consumption differs or not.
Breakup, marriage breakup.
Sorry.
What breakup I say? Oh, is it marriage breakup, right? Or something different?
No, no. It's a simple relationship breakup data set.
Okay,
So the data set contains the breakup dot is called breakups.csv,
okay,
and
got it.
the alcohol consumption pattern is observed before and after the breakup. So again, uh, here we have used a disk plot. We can use a his plot over here or histogram plot over here. And while using the breakups data set and before and after breakup values in within the data set, we get the statistic value of minus 0.53 and the probability value of 0.59. That's just- So if we go by the implementation of the t-test for the pad sample test, we get the value of minus 0.53 and probability value of 0.59. Now, as the probability value is 0.59, which is more than the value of alpha that we take, which is 0.05, we can say that there is no change in the alcohol consumption pattern before and after the breakup. Now, moving further with the chi-square goodness of fit, chi-square goodness of fit test. So chi-square goodness of fit test is a non-parametric test used for comparing the observed distribution of data with the expected distribution of data to decide whether there is any significant difference between the observed distribution and the theoretical distribution. So let's say uh, we have an observation which is an actual observation, and the expected observation or the that or an observation that we believe it to be true. So this chi-square goodness of fit test is used about when we are uh, dealing with and checking the validity of an actual observation and the observation that we are led to believe for whatever kind of reason. So mathematically stating chi-square is denoted like this, with the summation from I equals to 1 to n, OI representing the observed frequency, EI representing the expected frequency, whole square divided by EI. So in this, to understand the chi-square goodness of fit, we'll be taking an example of an airline, and uh, what the passenger, which kind of food passengers prefer, and the captain cook, which happens to be the operations manager for the airlines. He has a belief of a certain percentage of passengers preferring certain kind of food. So a sample of 500 passengers was chosen to analyze the food preferences, and the observed frequencies uh, are stated. So vegetarian has 190, 185 for non-vegetarian, low calorie for 90, and diabetic for 35. The operations manager thinks or expects that 35% of their passengers are vegetarian, prefers vegetarian food, 40% prefer non-vegetarian, 20% prefer low calorie, and 5% requested for diabetic food. So we'll be taking the alpha as a value of 0.05. The null hypothesis is the belief of our Captain Cook, and alternate hypothesis is not what Captain Cook believes. So we'll be using the chi-square method, chi-square method for the stats model, from the stats model, which takes two parameters. One is the observed frequency, and the other one is the expected frequency. So in order to get the observed frequency, we have it 190, 185, 90, and 35. The expected frequencies were given in percentage for 500 passengers. So we'll be converting them and stating them in the list of expected frequency of for expectations. And then when we print the values, these are the values that we get from 175 to 25. Now carrying out the chi-square goodness of fit test for the observed and the expected frequency, we get the statistic value of 7.4 and the probability value of 0.059. So this is the same kind of implementation as in slides. We just simply converted the percentage values into actual values, and we got this for our expected frequency. And then when we got carried out the test, these are the statistic values that we get. So as the probability value is more than 0.05, we will retain the null hypothesis, which is the original claim of Captain Cook for the frequency or for the belief of his percentage values of the passengers that they prefer, what kind of food that they prefer. Now, moving further with the analysis of variance or ANOVA. So we were dealing with different kind of changes in the previous observations for chi-square, for a paired sample t-test, two sample, then one sample t-test, and the z-test. In ANOVA, it is used to compare mean values simultaneous for more than two groups or samples created using a factor or factors. So, for example, we can say that there is a discount on a same product, but the types of discounts are different. So, as stated, 0, 10%, 20%, and we want to see the changes on what are the changes of sales for different discounts, 0%, 10%, and 20%. So one-way ANOVA is used to test for differences in the means of three or more groups. It is employed when investigating a single factor and a single dependent variable. Limitations include the requirement for normally distributed dependable variables within groups and homogeneity of variance. Just a second. So the test compares population means and is useful for scenarios like quality control and in production processes.
It means that
So we'll take this. Sorry.
if there is a difference of discounts to three groups, and we are trying to say that there, because of that, we may have better chances of
So
selling. What?
let me put it this way. There is a product. The same product is used for different discounted prices. So
Okay.
what we want to uh, observe is that the difference in the sales or the average sales for different values of discounts. So what will be the average sales for at 0%, 10%, and the 20%, and what are the differences?
Good. Thank you. That helps.
So uh, we are taking the same example for the discounted price of a product. Here we are taking for uh, a product name Enzo's detergent powder, and they are giving a discount on of 0% or no discount, 10%, and 20% on randomly selected days. The quantity is in kilograms, and of Enzo sold in a day under different discount levels. So, conducting a one-way ANOVA to check whether the discount had any significant impact on the average sales quantity at alpha value equals to 0.05. So what our null hypothesis says is that there is no change, or sorry, not no change, but all the mean values for the different discounted rates are equal. The alternate hypothesis states that the mean values, all mean values are not equal. So the for the alternative hypothesis, it it should also be noted that mu1 or mu3 can be equal, or mu2 or mu3 can be equal, but not all three of them are equal. So this is the table that we talked about. If we go for the sales for no discount, 10% discount, and 20% discount, these are the kind of values that we get for randomly selected days of the detergent product. So when we plot the graph, of course this is a disk plot, but we'll be using the histogram plot. This is how the plot might look like. We'll be using the F1 way. Sorry. From the SciPy's stats model, we'll be using the F1 way, which will uh, which will give us the value for ANOVA. So uh, this is our null hypothesis. This is our alternative hypothesis. When we plot the graph, this is how the graph we get for our plotted values. And this is the DF or the data frame that we have created for reading the file. So using those from using the columns from this data frame, we have column for zero discount or no discount, discount at 10%, and discount at 20%. We get the statistic value of 65.86, or the ANOVA score for 65.86, and the probability value of 3.821. But please always make sure at the end of the digit that it's an exponent to power minus 18, so 10 raised to minus 18. So we can say that the probability value is equals to 0. So As the probability value is less than 0.05, we reject the null hypothesis and conclude that the mean sales quantity values under different discounts are different. So to summarize this session 3, 3.2, we discussed about the central limit theorem, then we discussed about the hypothesis testing, then we discussed about a framework to conduct a hypothesis test under. We discussed different types of tests, Z test, then one sample t test, two sample t test, paired sample t test for different values and for different situations. And we also discussed different examples under those tests. Then we discussed about the chi-square goodness of fit test, where we took the example of airplane service. Then comes the analysis of variance, and that was the last topic that we discussed for module 3. We discussed about the sales of at a selling price of a product under different discounts and watching the difference of the mean values of the sales of that product. So this is it for module 3. The module 3 whole comprised of different distributions. It started with in 3.1 and we concluded 3.2 with central limit theorem to different hypothesis tests to conduct. The next module that we'll be starting with is module 4, which is on linear regression.
Sure.
So thanks a lot for this is it for this sessions.
Yeah, Jaymeet, one question to you. Did we cover probability before?
Sorry?
Previous one was probability?
Yeah, probability and distribution. It was 3.1.
3.1, okay. So this is next one is going to be linear regression, which is getting into really the what do you call the ins of the machine learning.
Yes.
Good. That's good.
Yeah.
So I think we are done with the Python. We are done with all the preliminary stuff. So henceforth, everything will be on the machine learning, right?
Yeah.
That is good. So I hope people who are attending at least go back to the older ones, because we have covered Python. Because one of the problem with the machine learning is if you know one language, and that is most commonly used is Python. So therefore we tailored it to make sure that it is machine learning with Python, using Python. So I
Yes.
hope Jaymeet is doing good justice, and hope you can also have any question. If you have, please do. And make sure that you can go through the past recordings. All recordings are up to date. Even this recording will be posted by midnight. So you can be sure that you always have, this is the module. We only have covered 5 sessions, 3 on the one on earlier 2 weeks were more on the Python to get the Python 101, and then this is machine learning using Python 101. So this will continue for another 7 weeks, I believe. This is the second week, so we have 8 weeks, 24 sessions, 3 per week, Monday, Wednesday, Friday evening, and all are welcome to join. Those who want to, of course, give certification and all that, they have to register. Otherwise, you can always audit it out. As we call, auditing is for free. We have no questions on that to anybody. Anybody can join. So there are no restrictions. But if you want to get certified and pass the exams and all that, that will be separate. So that is the only thing which is paid. But otherwise, even we have another, what you call guest also, some discounts also. Yeah, Rakesh, go ahead. You have some questions?
Yeah, actually, I got notification by mistake on Meetup. So, is there any particular WhatsApp channel, something where you can send a notification for the session?
So what I do is normally we do it on the meetup, and since this is a continuous ongoing process, every Monday, Wednesday, Friday, irrespective of anybody there, not we always Jaymeet records it. So,
Okay.
and the same link is used every time.
Okay.
So if you have taken today's link, that is used for next Wednesday also, same thing. So sorry, next, that is for a Friday. So Monday, Wednesday, Friday, we use the same link. We just announce and we send a notification last minute, but all the time it is the same thing. Okay, no different. This is to ensure that people are attending regularly and taking advantage of it. However, if you want notification, yes, I will do it. Rakesh, what is your name? You put the email in the chat window. I'll make sure that you get it.
Yeah, I can do right away. Just give me a second.
Yeah.
So, just one more question. So, ultimate goal of this is to completing the machine learning, correct?
Correct. Absolutely. Yeah. So machine learning, we have got modules. So we have a recommended book also if you want to observe. So everything is there on the. So you can go to the EOTF link, and we have defined what the course will be, what chapters we are covering and not covering. So you can follow through the book also, as well as you can follow the classes, so that if you want to solve some exercises, Jaymeet is already handling the what you call the Jupyter notebook. So most of the exercises are on Jupyter notebook. You can even go through the book and follow it. So sure, you are welcome. Go ahead. Any other question?
No, that's all actually.
Yeah. Thanks. So check your email, and I'll take care of it. Okay.
Yeah, already given.
Yeah, thanks. Jamie, go ahead and take care of the thing. Pass it.
Rakesh, it has been deleted. So can you just
I sent you private actually. Jaymeet Vasava, correct?
Yeah, yeah, okay. Otherwise, you send it to me. I can take
Okay.
it private here. That's okay. Yeah, you can do private. Yeah, we don't want to expose anybody. And I will stop the recording in the meantime. Sorry, I forgot. I'll let me stop the recording.